Good evening, star nerds. Welcome to tonight's episode of the Astro Imaging channel. Tonight we have with us Dan Champion, who I saw give this the similar version of this talk at the Rocky Mountain Star Stare a couple weeks ago, and it was awesome. So I invited him to come on the show, and you might melt your brain a little bit, but it's really cool, I promise. And at least some folks I think will be interested in actually giving this a try. This computational astrophotography. Before we get to him, just want to mention our upcoming shows to get people excited about them. Next week we have Steve Ziegler with talking about the April eclipse experience, his experience with the April eclipse. Did we ask if you were going to give 30 seconds on that, or I can't? Oh, I don't know.
No, but I can.
Yeah, sure.
Okay, great. Yeah, so thanks, Molly. It's great to come back for round two. I spoke back in September before the October. That would be right before the October's annular eclipse. So I'll cover that too. So I made it to both eclipses, and after my last talk, Patrick and I were sharing, and we thought maybe it'd be a good idea to come back. So what I'll do is I'll talk about my experiences, share some information, share some images, hopefully share some video and some techniques. I know there's a lot out there right now about eclipses, so I hope to bring something new to the table. Please come by next week. You'll see if I do or not. So I'll see you then.
Awesome. Yeah. And we'd love to hear more about eclipses. And plus, this can help you plan for your 2026 or 8
Yes.
or other future eclipses if you're going to go abroad.
Yeah.
So let's see. Sunday after that, we have Mike Tyvalma, talking about the ASI Air, which is a little miniature computer that a lot of people have been using, has been getting popularity, a Raspberry Pi based device from ZWO. I'm surprised we actually haven't had to talk about it yet, so we'll get to hear a little bit about that. And then some other talks on PixInsight scripts coming up, AI in processing, and another Nina plugin talk about using the sequencer power-ups after that. And that takes us all the way through Labor Day, where we're going to not have a show that weekend because it's Labor Day and half of us probably will be out doing fun things. And after that, our schedule does clear out quite a bit. So if you are interested in coming on and giving a talk about a cool device you have, a technique you use, an experience you've had, like we've really, if you see all of our past shows, you can see we cover quite a wide variety of topics. If more beginner, more advanced, somewhere in the middle, we need them all. So you can hit the contact us button on our website, theastroimagingchannel.org, and shoot us an email with your proposed topic, and we'll see if we think it'll be a good fit. Let's see. I think that's about it for announcements. Obviously hit like and subscribe, as people always say, on YouTube, so that we can continue to get our content out to other people and get more people aware of our show. And I think that's about it. So Dan, take it away.
Right. I'm going to start this share here. And thanks again for having me. This is a topic that I find pretty nerdy and pretty interesting, so I hope you all will enjoy it as well. There's a few handful of topics that we'll cover. When I first wrote this presentation, I had a hard time coming up with the title. So you will learn about, or there'll be tie-ins to pretty much all of these topics here. Computational astrophotography, doing the processing with Python, taking a scientific imaging approach to astrophotography processing, automating and accelerating things with the GPU, and sort of doing it at the same rate that the data is arriving. So a lot of different topics here, and we'll touch on pretty much all of them here. And there will be a demo as part of this, so you'll see some of this stuff in action. So, all right. So I just wanted to mention again, thanks for giving me the opportunity to talk. I actually was partly or mostly inspired going down this route through a TAIC talk from the past that many of you may have watched. It's Richard Wright's "Why Guiding Needs to Die and How It's Going to Happen." That talk touched on a lot of big ideas about how computational astrophotography could potentially change some of our workflows and be a game-changing capability for the things you can do with processing. At the time, I was already working on some Python-based astrophotography processing tools, but after seeing that, the ideas about going towards real-time GPU acceleration and really pushing the limits of what you can do when you throw ridiculous amounts of compute at this problem, just to open the doors and do more innovative things. So a little bit about me. I'm new to the Astro Imaging channel. I think this is the first talk I've given here. I've been doing astrophotography for quite some time, however. I started with film and early DSLRs, using all of the usual tools, Photoshops and GuideMaster and all that good stuff. However, in around 2012, I moved to the East Coast, and the dark skies are few and far between out there. And I kind of left the hobby for a little bit, or let it sit for a while. And relatively recently, I started getting back into it, and I was pretty blown away by the advances in software and automation that were out there. However, at the same time, I was definitely a little unsatisfied that the processing being done in astrophotography was still predominantly being done with manual processing tools and GUI interfaces for that type of processing. This sort of contrasted with the way I usually approach things. My background is in scientific imaging and data science and math and physics. And when we do scientific imaging and those sort of industry applications, it's all in code. We code up our algorithms, we vet them in code, we test them, and we leverage the repeatability in that sort of scientific process to get the best possible results. And I wanted to bring that to astrophotography. But anyways, that's a little introduction here and where this came from. Today, we're going to start with me introducing this Python library called AstroComPYute. Then I'll sort of discuss what you can do with AstroComPYute as far as computational astrophotography workflows, pushing work to the GPU. And then we'll talk about some of the real key or critical components to this computational astrophotography approach. We'll have some really nice examples. Always good to show some things that the tools can do. And then we're going to take a deep dive on one particular aspect that I thought would give you a lot of depth in one area that really shows the game-changing things you can do with this software approach. And then I'll show you where some references, where to get stuff, that all the code's on GitHub, and all that info will be provided. By the way, these slides, a version of them is on GitHub as well, on the GitHub page for AstroComPYute. So if you're interested in that, you'll be able to find them in the future. All right. So one of the motivating things for me a long time ago, especially after watching that TAIC video about computational astrophotography in the past, was sort of taking EAA to the furthest extent possible. And what that meant to me was holding a electronically enhanced apparatus up to the sky. It could be on a mount or whatever. And in real time, you see the fully processed astrophotography result. So this departs from traditional EAA workflows by actually doing all of the post-processing in near real time. How could we do that? Do we even have the compute necessary to do that? And are we fighting up against physics in order to be able to accomplish such a thing? The answer to that is we barely have enough compute, and yeah, we are butting up against physics, but there are some tricks that we can do to get around that. So this slide sort of shows some of the very basic noise calculations that are typical of our astrophotography data. Let's see if I can turn on my laser pointer here. So you all have probably seen this before. Actually, the last TAIC talk had a lot of details along the same line. So I would recommend watching that one if you're interested in these topics. This is just touching on the surface. The idea here is we have a Poisson process that's generating the photons that are arriving at our detector, and they're arriving at some average rate mu. But because of the random process, there's noise in our observed photon detections. So sometimes we detect a few more, sometimes we detect a few less. One of the fundamental properties about these Poisson processes that are typical of low light photography and extended nebula objects is that the variance of that process is equal to that mean arrival rate. So this is the fundamental property of a Poisson process. And with this alone, you can actually calculate what the relative uncertainty in us being able to estimate a very dim amount of a pixel in our image that corresponds to some very dim nebula. And it's the square root of that mean arrival rate of photons divided by mu, or 1 over root mu. So this is problematic because as mu gets very small, as the light gets very dim, the relative uncertainty gets very large. And so we have to use subframes in order, we typically use subframes in order to overcome that. And when you use subframes, especially if the numbers are approximately right, these things are can be approximated by a Gaussian, and you can get this sort of square root of n law reduction in uncertainty. And that's what's happening with our subs, is we're accumulating those subs, and then we're reaping the rewards of that square root of n reduction in our uncertainty, and then the low photon arrival count pixels, we're more able to accurately estimate them. So this is our trick, is in astrophotography, is doing that. This is a problem, though, for trying to do things very fast or in near real time, because we don't have a whole lot of photons. We have very few subs if you're trying to do this very quickly. So we have to start thinking outside the box about how can we exploit this relationship here without breaking the laws of physics. So one thing is to just increase n. So and some of these are palatable, some of them are not. So you can do more subframes. That's sort of contrary to doing astrophotography in real time. And the other idea is using nearby pixels. So that requires the computation here. So that's algorithms like noise reduction or star separation, and the subsequent processing that star separation allows you to do. Also, probably the most heavy-handed approach is binning. But these methods, the computational methods, allow you to use the information in nearby pixels to artificially increase n. Another way to go about this is to increase mu, and the one way to do that is with faster optics and longer exposures. So you can, or effectively longer exposures, but some of these are contrary to our goal of trying to do this very, very fast. But fast optics is something that we can definitely leverage. So the question is, do we have enough here? If we combine fast optics with a modern detector, an 80% quantum efficiency detector, and we pull out all the tricks, like characterizing everything we possibly can with our apparatus, and leveraging a gargantuan amount of compute to leverage that information by nearby pixels to artificially increase n. Can we get in astrophotography post-processing to work with very few subs, and also can we get it to work really fast? So that's what this is all about, and hopefully I'll convince you that we can make some good progress here. There's one thing to note here, is that this faster optics in the sort of in the vein of the Dragonfly telescope strategy, if you're familiar with that, where you're using multiple imaging chains. This is one ultra cheat code here, because with multiple imaging chains in the same period of time, you can collect essentially arbitrary amounts of frames if you have that many imaging chains. It's of course very expensive to have parallel imaging chains, but this is one method that you can use to increase your effective F ratio, which is a pretty exciting opportunity. We'll talk more about that later. So, all right. So in the pursuit of this, I created this project called AstroComPYute. It's an open source Python-based full end-to-end astrophotography processing toolkit or library. It leverages a lot of the open source Python image processing and Astro related projects that are already out there. It's CUDA accelerated, and it runs on OpenCV as well. So if any of you have done scientific imaging before, you've probably heard of a lot of these tools, and we make use of them in AstroComPYute. It can effectively run about as fast as the data is arriving, usually. We'll see a demo here a little bit later. And what I mean by that is in about 10 seconds, you can process a 26 megapixel image end to end. Now, if you're going to do additional processing, you can always do more and more processing. You might need more processing time. So now there's some requirements for the software, and NVIDIA GPU is one of the key requirements here. CUDA allows us to do really amazing image processing tasks on the GPU device. And right now, there's CUDA is the biggest name in town when it comes to doing general purpose compute on a GPU. We'll talk a little bit more about that on the next slide here, but that's one of the main requirements here. I'm also using pretty late model hardware, but I'm already out of date as of the end of this month, and especially later this year. The hardware is going to be a heck of a lot better than what you'll be seeing today. And there's some software dependencies like, of course, OpenCV, CUDA, the CUDA toolkit, NumPy, SciPy, scikit-image, AstroPy, some Python projects, but also helper software. So AstroComPYute has Python wrappers to allow you to interact with ASTAP and Starnet++. So there's to allow you to do star-separated processing and also plate solving for various purposes. And then one of the things we'll talk in the deep dive about is the usage of reference materials from NASA and what's called WAM. These are all sky survey results, and we'll talk more about that a little bit later. So I'm running this on some pretty fast optics, usually f2 or faster. There's an example behind me here. This is an f2 Nikon lens. I also use an f1.4 lens, as you'll see a little bit later. And I've also tested out some even faster lenses like f1.2 and that sort of thing. And that's, again, trying to exploit all those properties and the physics that we're bumping up against. And I'm using usually Nina for image processing, and this project doesn't handle data acquisition. You choose whatever data acquisition you like to use, and you point AstroComPYute and use one of the AstroComPYute scripts or libraries in order to do what you want to with it. So anyway, here's the link in the GitHub. I'll show you this again a little bit later, but go and check it out if you're interested, and you'll see the stuff that I'm talking about today. So. All right, so AstroComPYute has some very specific strategies, goals, and themes. So scientific imaging approach, trying to do everything reproducible, scripted, and procedural. The idea is we want to be able to have a documented end-to-end script that you can hit go on, and it will perform the processing, and you could run it again without having manual input. That allows you to change variables and pull out algorithms and put different ones in to test out different noise reduction algorithms or whatever. That's sort of the part and parcel to that. Another one is an open source software approach, trying to get away from proprietary solutions, and you'll see a little bit why later. It really allows you to tap into the best available tools that are out there in this industry. And then one of the things we're going to try to do is solve as many of our hardware problems with software. And this gets into that previous TAIC video or talk about this topic, which is like kicking guiding to the curb, because it's a software problem. We don't need hardware to solve that problem. And then whenever possible, try to solve problems with before the fact apparatus or data characterization. And you'll see some advantages to that. We all kind of do that, or some of us have in the past when you create things like master flats and master darks, but you can do a whole lot more. And I hope to convince you a little bit more of that. So anyway, so these are some themes. You'll see me coming back, like, why would we approach it like this? It's because we're trying to leverage one of these goals. So, all right, so talking a little bit about astrophotography processing from a compute perspective, and many of you already know this if you're doing post-processing, it's pretty intensive on your computer. But here's some interesting numbers. This is all for floating point 32 calculations, which is pretty standard for image processing tasks in tools like Photoshop and PixInsight and that sort of thing. Modern CPUs can do about 100 to 200 gigaflops per processor. So that's billions of floating point operations per second per processor. So 100 to 200, keep that in mind. A modern GPU can do orders of magnitude more gigaflops per second per device. You can see there's a lot more zeros here, 10,000 to 83,000. 83,000 right here, that's the NVIDIA RTX 4090 right now. And this is about to be eclipsed in the later half of the year with the Blackwell series, which is going to be a huge bump on this number again. So if you look at these numbers, that's billions of floating point operations. When you consider the operations we do with processing, it's usually around 1 to 10 gigaflop per operation for simple processing steps. This is like doing simple arithmetic on an image. Flat field, dark field corrections are classic examples of that. Stretching and color correction and hue, saturation, and value type adjustments. These all take around 1 to 10 gigaflops per step. And we, in a full end-to-end workflow, you have several of these, so they sort of accumulate, but they're pretty small. You can handle that in sub-second usually with a single processor, and then no problem. The problem is the complex processing steps. So these are like some noise reduction filters, AI tools, registration, locating stars, and gradient estimation. All of these can require 1,000 to 10,000 gigaflops per, or can require orders of magnitude more gigaflops here. And when you sum all these things up in a pretty typical workflow, we're talking around 1,000 to 10,000 gigaflop to do the end-to-end processing. And that can be a fair amount of time on a processor. But if we can leverage even a fraction of the compute available on the GPU, this is no problem. So anyway, this gave me hope that this was going to be really feasible if we could leverage the GPU to do a lot of our hard work for us. So in this, I mentioned this before, leveraging the open source. If you compare some of the closed ecosystems to the open ecosystems, there's really no comparison. This project makes use of all of these tools in one form or another. These are all Python libraries or powerful binaries for doing image processing, or packages like cupy that allow you to leverage the GPU for general purpose compute using Python very easily. And then there's a whole ton in cottage industry of astronomy specific tools, like AstroPy is amazing for doing a lot of sort of core operations. AstroAlign is really cool for doing registration. And then there's tools like Starnet++, which don't necessarily have Python APIs, but we can easily write Python wrappers to interact with them. And we did that for Starnet++ and also for ASTAP. So we're trying to leverage all the work that goes into these. These libraries are kept up to date. There's thousands of developers contributing to them, and they have by using these, you have access to some of the most cutting edge algorithms out there for doing image processing tasks. And you're only going to be able to access a small fraction of those and tools like Photoshop and PixInsight and GIMP and that sort of thing. So that's one of the reasons we wanted to go down this route, is to tap into all of these capabilities. So the one thing that these libraries have in common is they try to perform an operation, do it really well, and make its outputs usable by downstream operations. So that enables you to use a tool from scikit-image and then jump over and use a image processing function from OpenCV, and then push that a next operation to the GPU and use cupy in order to be able to do that. It's because we're able to use the outputs from one operation and put them into another. So that's sort of what we're capitalizing on here in order to get access to the best tools. This is an example astrophotography workflow that you can do in AstroComPYute. I'm not claiming this is the correct way to do astrophotography processing, but it's an example of what you can do with AstroComPYute, and also that performs this sort of end-to-end operation. So you can see at the top it begins with image capture. This is handled through your data acquisition software like Nina or something like that. And then it goes through a sequence of file I/O, CPU, and GPU operations. So you're reading the data, flattened field and dark field corrections, determining star locations, registration and dewarp, updating image stacks, cropping, gradient estimation, color deconvolution or color correction, noise reduction, histogram stretching, star removal with a tool like StarNet++, star reduction after you've removed them and on the star only image. And then there's actually more steps in here, like additional noise reduction steps once you get into this star separated processing, and maybe some final saturation and value adjustments. So this is an example of a fairly end-to-end process here. And I've indicated sort of the pieces of information that you might need access to, or it would produce during the workflow. So you're maintaining a stack. You've pre-computed a master flat and a master dark. You've pre-computed a color deconvolution matrix to do color correction. And all the while you can be saving off star-only images so that you can use the star-only image on subsequent processing iterations if you want to. So as you can see here, I've indicated some of the steps that you can offload onto the GPU. And some of them are really important, which I've indicated with stars, the asterisks. These are the heavier compute tasks. And the difference between doing CPU processing and GPU is, about 1 to 2 orders of magnitude in runtime. And it really enables you to do these steps in sub-second or in single-digit seconds. I think the longest runtime of all of these steps is in gradient removal. Which is gradient estimation and removal. It takes about 4 seconds for a 26 megapixel image, and it can probably be sped up even further. But compare that to CPU runtimes, and it can be night and day. So some of the critical ones here. So we're going to be using the ASTAP command line interface as part of one of these early processing steps to determine where the camera is pointed, and that has some huge advantages that we'll talk about. As part of the plate solving, we can compute the celestial coordinates of every pixel on the camera. We're going to make use of some pre-collected all sky survey results from NASA, the Deep Star Map and the H-alpha full sky map. We'll talk about that a little bit later. Those are going to be used effectively for gradient removal and background estimation. And then there's we pre-compute the color calibration matrix, and we do fast noise reduction on the GPU, which is one of the accelerating components of this processing pipeline when you do star reduction and star removal. And that's the last one right here, is leveraging a StarNet++ wrapper to be able to do a star separated processing as part of this Python-based workflow. So these are some of the core or key components here that really make it a full end-to-end process option. So some of you may be wondering, is this EAA? Is it not EAA? I just wanted to mention that SharpCap is a great, easy, and accessible tool. AstroComPYute is not trying to compete with that. This tool is for Pythonistas, or people who have a Python background and who are into automating some of these processes. So one is in code, the other is a data acquisition and combined graphical user interface environment. So two very different tools. And I just wanted to sort of contrast what an EAA approach might do with what an end-to-end processing tool might do. And AstroComPYute is more on that end-to-end processing and a scripted approach. And I just wanted to, AstroComPYute is not alone. There's a few other projects that are out there. I found this Jaeger.io Astro project as well as David Strickland's astrophotography project on GitHub. There's a couple of them out there, but it's not as common as I thought it would be. And AstroComPYute definitely pushes the limits and takes it further. And hopefully it will, provide some unique values out there for people who are interested in this type of approach. So. All right. So
Dan,
I'm going to show. Yeah, go ahead.
We have a couple questions before you get
Sure.
into your examples. Josh asked, does this run on Linux and Mac?
Yeah, there's no problem running this on Linux or Mac so long as you have an NVIDIA GPU on that system. That's not a problem at all with Linux. I've actually done CUDA on a Linux environment before. For Mac, I'm not aware of all of the flavors and options of GPUs that hardware supports. I imagine if you had a Mac Pro desktop, you could probably put in an NVIDIA GPU. I could be wrong. Maybe there's other GPU options out there for Macs, but I don't see anything that would prevent you from doing this because it's all Python based. So long as you can install from the PyPy and also get CUDA working, you'll be good.
Isaac asks, does this work on an AMD GPU?
Yeah. AMD GPU, possibly not. Cupy has experimental support for some AMD GPUs, but I think there'll be some growing pains there. So I would probably say probably not going to work with an AMD GPU right now. In order to leverage CUDA, you have to have an NVIDIA GPU. So.
And Isaac also asked, what is the color deconvolution matrix?
Good question. Color deconvolution matrix is a way of doing color correction where you take pictures of known answers and you compute a color correction matrix that you can apply to your data to improve the accuracy of the color rendering. I'll show you some examples a little bit later if there's more interested in that. That's a deep dive in and of itself. So it's one way of doing color correction. So.
And have you ever thought about wrapping a GUI around this whole thing?
A little bit. There's actually a couple GUI components as part of this project. One of them is a tool that allows you to compute those master flats and master darks. I've thought about making a GUI that helps you calculate that color calibration matrix as well. It might make sense to do a GUI where you can actually see the live processing and interact with it in some way, but it's mainly, it lives in a script, and you'll see a little bit that it's more like a notebook style programming. So.
Okay, thank you.
No problem. All right. So I think that was a good break. I had an inserted break for questions a little bit later, but we took care of it a little early. So here's some example processed images. On each of these, the amount of integration times in the upper left. And in general, as I go through these examples, I'm going to be showing you shorter and shorter total integration times so you can see what you can do with very few amounts of subs and very few seconds worth of data. This is, of course, the Orion, Orion Nebula and Horsehead Nebula and Barnard's Loop. This was 100 subframes at 10 seconds in a super dark site in Hawaii. This was with a f1.4 105 millimeter lens, so it's very wide field, very fast, shooting wide open, no filters, and it was using a cooled ZWO camera, so getting into good quantum efficiency there. But it was a color Bayer matrix camera. 1,000 seconds. This place was super dark. The thing I remember about it was how annoying the zodiacal lights were. They were very bright. Here's a little zoom in there. You can actually see this green artifact right here. That's a hot pixel because I'm using master flats and master darks lifted in there just so you can see it. But renders pretty well. And this is that going through that workflow that I mentioned before. This is the Carina Nebula, also 1,000 second integration. Same camera, same lens, very similar setup there, although this one was only about 5 or 7 degrees above the horizon. So it just barely gets above the horizon in in Hawaii there. So here's the Heart and Soul Nebula, also 1,000-second integration with the double cluster right next door. This was 200 subs, 5 seconds each, but otherwise very similar setup in a Bortle 4 area near Las Vegas where I live. So here's the North American Nebula. This one's 500 seconds. So this was 100 subs at 5 seconds each. All of these are unguided, by the way. I forgot to mention that. I'm really channeling that guiding needs to guide ethos there, because when you're shooting 5-second subs or 10-second subs, you can just solve the registration and guiding with software, and we're sort of proving that that works just fine right here. So all of these examples have been star-reduced processing results, so also keep that in mind. But this was this data was collected at RMSS in the Rocky Mountains in 2023. It was Bortle 2 or Bortle 3, pretty dark site, but a slightly shorter exposure time. So this was 500 seconds of the dark sharp. You can see the dark sharp and some of the surrounding dark nebula around here. 100 subs, 5 seconds each. This one was 250 seconds. The Rho Fishy Cloud Complex, 50 subs, 5 seconds each. Same camera, unguided, and this was also in the Rocky Mountains in 2023. And then this one was 130 seconds, which was just sort of silly. The Eagle, Swan, Sagittarius Star Cloud, the Trifid Lagoon Nebula, the 26 subs, 5 seconds each. So this is getting down into silly fast. So 130 seconds is about 2 minutes. That's a very small amount of data, but we're shooting at f1.4. So this one's more recent. So I took this one. This was also in Hawaii, but I processed it for this talk here. So this was 100 seconds worth of integration. I might do a demo of this one a little bit later. 10 subframes, 10 seconds each. And showing you sort of what you can do when you do some additional processing. And this was a very recent example. I collected this in my backyard just like a week ago during first quarter. So the moon was out, and I was shooting at 200 millimeter this time. So this is a different lens, and I was also in my backyard here in Las Vegas shooting through a tri-band filter, and I'm still pretty impressed with what you could do with 500 seconds given these conditions right here in Bortle 9. So with just about 10 minutes worth of data. So all right. So this is where I was going to pause for any questions. I'll still do a quick pause here. Is there any other quick questions before I go down in our deep dive? So,
yeah, one more came up. When you stacked the images, was there any rejection performed?
Zero rejection. That's something that I think you could add into this workflow. I use Nina, and Nina does some star calculations, so you could do some rejection based off of the results from Nina. Because those are embedded in the header and also in the file names if you want them to be. But for all these examples, I did zero rejections. Shooting at 5 seconds, it covers a lot of crimes because you don't have to rely on very accurate guiding at all. So.
He might have
but
also
if an
been
airplane goes through it, or a meteor, or
pixel rejection, and might be what he was referring to.
yeah.
Gotcha. Yeah, when airplanes fly through, I just let them fly through. They'll dim out as you integrate more, but not much there. But for pixel rejection, I don't do any of that. So cool.
Hi Dan, this is Jaime speaking. How are you?
Good.
How do you deploy actually these? I mean, for example, do you need to have your CUDA-enabled computer next to your telescope, or could you work in certain kind of network? How do you deal with the deployment? Yeah.
Yeah, I think it would be really exciting to try to do a remote deployment. I personally bring my sort of miniaturized desktop PC out to the field with me. It requires a lot of power. That a desktop PC will draw 400 to 500 watts, especially when you're doing GPU processing. So you have to bring power with you. But that's how I personally do it. I think it would be really cool to try to do it remotely, where you if you have a good internet connection, send data to the cloud, and then you could work with other people and leverage the GPUs in the cloud for this type of work, or send it back to your house and do your processing there. So.
Gotcha. Thank you.
Cool. All right. So one of the topics that I mentioned was particularly, a good example of this sort of computational astrophotography approach is gradient and background estimation. I think many of you have probably struggled or have pulled your hair out with this topic before, because it's such a critical part of astrophotography processing, especially in the world where light pollution gradients are very, very common. So I thought I'd go through this one as a deep dive to sort of show you what this Python-based approach allows you to do that is kind of like cheating and breaking the rules. I think you'll get into it. So as many of you know, gradient removal is this process of removing a nuisance signal that shows up in our images. It can be caused by light pollution or sky glow or other effects. And it can be significant. This example right here, I stole from the Dark Shark example that was in the previous slide, one of the previous slides. So that was shot in a Bortle 3 or Bortle 4 area. It was near the meridian, and this is sort of the scale of the background or the gradients that were present in the image. So for this, to sort of show you a empirical look at the gradients, I just took an enormously silly large median filter of the image, ran it on the GPU because they're really good at median filters, and just to show you the scale of the gradients that were there without having to estimate it through fancy means. And so what you're seeing here is that it was varying on the background at +5 to -5 ADU. ADU means analog to digital unit. That's like one detector count on our cameras. So the span here in the gradient was like 10 ADU. And that's as significant as some of the faint nebulosity, especially dark nebula that we're trying to capture with astrophotography. So we have to learn this surface here, this nuisance signal, and subtract it off from our data in order to be able to get a flat background that has that nuisance signal removed. So this is sort of the math problem that we're solving here. We have our signal that we want, but we have a noise term, a gradient term, and a background term. And the gradient term is spatially varying. The noise term varies with the intensity of the pixel. And then our signal is spatially varying. So we have to estimate this function right here from the data. And sort of the gold standard or the status quo is to sort of manually guide or select the sampling points in the background for gradient estimation. A lot of common tools take this approach where you have a grid of points or you manually select points, and then you let the software fit a function or a surface to your data, and then you subtract it off. And it's going to leverage the fact that these gradients have very long length scales. So they're smoothly varying usually, or they're very large features in the very least throughout our image, so that you can assume that these slowly varying signals in our data are the gradient and not the signal that we're after. So anyway, there's a bunch of hazards when you're doing gradient estimation. This little 3D plot shows you some real data from the Dark Shark, that Dark Shark example. The red dots are the actual pixel intensity values for my sampling points. And the black dots are the smooth black mesh that's within the field of red dots is my gradient estimate. So you can see the goal is to sample your data with these red dots and then fit a surface to it in one way or another. You have to watch out for several things. You have to watch out for stars and bright objects. You have to be very careful not to sample where your deep sky objects are. If you have high star density, like star clouds, if you're shooting near the Milky Way core or anything like that, you have to really be careful about star density. And then one of the other hazards is you have to be worried about computational complexity. It's really easy to run an inefficient algorithm on this problem because there's so many cool methods out there for fitting functions and surfaces and estimating non-parametric things, but they're often take orders of magnitude more time than we'd like to use for them. So there's sort of like good and fast, which is like polynomial regression. There's good, great, and okay fast, which is non-parametric regressors. And then there's great and slow, which is optimization-based regressions and solvers. So we've sort of gravitated on the faster side of things. Some takeaways here that, and I actually learned this from, I think, serial documentation, that fourth order polynomials are pretty much good enough for most gradients that we're dealing with. So that's good news. That means we can use faster methods. And I've had pretty good success with that. A counter example of that is when you have really bad gradients near the edges of your detector. But another one is extra edge sampling can be very effective because the gradients there are more visible and more common. Another thing is that there's really no unique solution to this objective. You might think that there's an objective like answer to that math problem I presented before, but we're doing astrophotography. There's an artistic aspect to it, and it is totally reasonable for you to use a background that suppresses certain features to bring out an object. So that's something that is important to keep in mind and to build in the extensibility of these tools in order to be able to handle. So in order to do this real time, you kind of have to do this autonomously. And it brings up the question or the comment that it would be just great if we knew where not to sample. If we knew where not to sample, this would be a whole heck of a lot easier. So there's a few ways that we've gone about doing that. This was the first sort of idea. It's not a deep idea. We wrote a Python wrapper for ASTAP so we could submit an image to ASTAP and get the annotations that ASTAP can produce. So then I wrote some image processing flood fill type algorithms to calculate a binary mask from the annotations that would essentially mask out anything that was annotated in the image. And if it's annotated, that means there's a deep sky object there, and thou shalt not sample the background in those locations. So that was kind of cool, and it worked. And with this example I showed here with the dark shark was this exact method. If you look closely on that 3D plot, there's a little hole in the center that corresponds to this big bank of purple pixels here, which means don't sample there. Purple means don't sample, yellow means sample. So this was cool, and it works. And the whole sky has been mapped out and has annotations for everything. So this is a cool tool that we should be using to help us, automatically pick sampling points. But when you think about this, we're only kind of scratching the surface here. Annotations is pretty much the minimal amount of information. I wanted to use a sledgehammer to solve this problem. So that got me thinking about all sky surveys. This sky survey, the NASA Deep Star Maps, is pretty amazing. It's like 2 billion stars from astrometric measurements. And it's available in just silly resolutions. And it's already prepared in celestial J2000 coordinates, which makes working with it programmatically very easy. So AstroComPYute, one of the requirements is that you go to the NASA download page, and which is, I think, shown right here, or there's a link to it at the references page. So you go to the NASA Deep Star Map downloads page, you download the star map, and then when the first time you run AstroComPYute, it will pre-compute a fast interpolator that can be rapidly evaluated at plate solve solutions. And then it'll take the celestial coordinates of every pixel in your image and then and evaluate them at the NASA Deep Star Map. This can be really useful for seeing high star density and star clusters and informing you where not to sample. So another one that's great is the H-alpha full sky map. This is another sort of long-term effort to map out the H-alpha presence all throughout the sky. This WAM effort right here was in the northern hemisphere, and they actually moved that same equipment to the southern hemisphere and to get full coverage, and then they supplemented it with some other things. There's a few areas that have some lower resolution than others, but overall it's pretty amazing. And it gives you this all sky H-alpha map at very coarse resolution, just like 2.5 arc minute resolution. So AstroComPYute, again, the first time you run it, pre-computes a fast interpolator so that you can evaluate the H-alpha map at every pixel of your image in about a second. So, and that can, again, inform of where you're going to sample for your gradient estimation. So this is only available in galactic coordinates as far as I could tell. So here I've converted it to celestial coordinates using the AstroPy celestial coordinate tools, which is amazing. So anyway, so this looks more familiar to that previous one. So I think that's fine. But anyway, all right. So I'm going to show you sort of what AstroComPYute looks like in action, step by step. And then I'll show you this live demo. So this is kind of what AstroComPYute script begins like. You import the libraries and methods and functions that you're going to use. AstroComPYute has several modules. Some things like a priori is all the things that you can pre-compute in advance, like the star maps. File I/O, image math, registration, correction, filters, enhancing, and color corrections. They all have a module in AstroComPYute so that if you need to do something, you can quickly go find the module and get the tool out of it that you want to, or at least that's the hope. Then you define where your light frames are. And here, in this case, I'm just going to process a single image. And you also specify your master flat and master dark that you've pre-computed using one of the AstroComPYute tools. So after that, you load it, you read your image, and then you do a flat field, dark field correction just to get a field illuminated, a field corrected image to work with. And then the very last thing I've done here is just visualize it with this quick inspect RGB function that allows you to see it. It does a very fast, very simple linear stretch so you can kind of see what's in your data right here. So that's one frame of data of that Lagoon Nebula shot. The red arrows or chevron symbols are indicating things that you would modify. Obviously, you can modify this any way you want to, but if you wanted to do this on your own data, you would modify these where these red arrows or chevrons are. So, okay, so going a little deeper, after we've done that initial processing, you might want to plate solve it and get that deep sky annotation mask and that I was using in the Dark Shark. So this is what that looks like: is you call this function called plate solve mask. This is the ASTAP wrapper, and this produces that binary mask of where the deep sky objects are and aren't, and also produces an annotation for you if you want to add that into your images. One thing you have to provide for it is the path to your ASTAP executable. So there's actually two of them. There's the ASTAP executable, and this is a typo. That should just be ASTAP_CLI. There's the CLI executable. They do slightly different things. This one is just for very fast and easy plate solving. This one allows you to do things like annotations. So anyway, we use one or the other depending on what you're doing. So, but this does the plate solving and produces the mask. This just does the plate solving. So after you do that, with the plate solve solution, you can put it into this AstroComPYute function right here, which transforms the plate solve solution into per pixel celestial coordinates. So it turns out these plate solve solutions, they give the answer in the terms of coordinates on the tangent plane to the celestial sphere at the point that it is at the center of your camera image. So there's some geometry calculations to transform that tangent plane coordinates to the celestial sphere to get per pixel images, per pixel coordinates on your camera. When you run these things, you get the per pixel coordinates, and they're accurate to about 20 to 30 arc seconds. So they're pretty accurate at least on these wide field shots. I think you can do better if you have longer focal lengths. So. Anyway, so here I'm just plotting out some things to sort of show you what's going on along the way, the annotations and the mask. So after you've done that, you might want to go get those all sky survey results to help inform your gradient estimation. So here you tell it where your download file is for your NASA deep star map. It's this EXR file format, and AstroComPYute has a parser for it, or uses, I think, the OpenCV parser for EXR. And then when you call this the first time, it's going to create this fast interpolator called eval start map, and it's going to save it on your disk so that you can reuse it instantly in the future. And so then after you do that, you can evaluate it at your image, and then that produces your star map at image right here. That's the star map evaluated at the pixels of your image. So you can compare this image here to this one right there. That's the real deal, and that's what the NASA Deep Star Map is. This is all based on astrometric calculations, so dark means dark, and this is really good for informing you where your background estimation points should be. Same story for the H-alpha map. This comes in the form of a FITS file when you download it from NASA, and the same deal as before. The first time you run it, it pre-computes this interpolator and saves it to your hard drive so that you can use it again in the future. And then here I'm evaluating that at our image. So now we have the H-alpha map at our image. So this is just the H-alpha. Here's just the stars, and you can compare that to what we saw with a single frame. You can see this is incredibly sensitive H-alpha mapping here. Pretty cool stuff. So anyway, so after you've done this, you might want to do something with it. And it's up to you how you want to do this. But for the way I usually do it is when you have these mask arrays, in the case of the annotation Boolean, or if you have the H-alpha and deep star map, you can either threshold or normalize them to get a binary mask like this one. And here I've combined it with a star mask. So I've ran a GPU algorithm that finds every star in my image and then puts a little black dot over every star. So I know that if you're not in a star area and you're not in an H-alpha area and you're not in a high dense star cluster, then you can sample the background there. And that's kind of what's left here is all these white dots you're allowed to sample there. Another approach that we've taken is sort of normalizing all this information in a 0 to 1 sense, where 0 means sample more here and 1 means, or I guess it's the opposite of that. So 0 means don't sample there, and if you're closer to 1, that means sample the background there. And here I've zoomed in to just a little teeny chunk, and you can see that there's these little white spaces between the black dots, and there's these little, there's a little black disk that I've placed in the binary mask over every star so that you're sampling the background away from stars and stuff like that. So, all right, so this was sort of like a code walkthrough that you saw. Now I'll show you it in sort of a live view here. So let me escape out of PowerPoint. And so here I've got sort of my setup. I've already got all of the CUDA installed, which is the hard part, and ASTAP and everything. And I'm going to process this North American Nebula data set that is a pretty good example of this. And so this is a processing script, and I usually make one of these for, you know, every different sort of class of objects that I'm processing, whether they're in the Milky Way or out of the Milky Way, dark nebula versus, you know, other types of objects. And then I modify them and put in new algorithms as they're made. So the idea is you make it your own, and you can use whatever algorithms you want to use. And now it's a set thing. It's scripted so that you can rerun this on Tuesday and it gives you the same result. And it doesn't depend on 1,000 mouse clicks. So this is my North American Nebula script. It starts off by specifying your lights, your flats, your darks, and some sort of identifying name for what it is that you're processing. There's some, I always put some of my key parameters up here. This is one of the more key ones right here. So the star reduction factor. So if you set this to greater than 1, it's going to use StarNet++ on the GPU to do star separated processing. We'll start at setting it to 1 so you can see how that works, and then we'll stop the processing, change that to 2.0, and then do star reduced processing and star separated processing. So and then I have it set to produce a live figure every 5 subs. So every 5 subs it's going to produce a live figure. So the rest of these things are like where your ASTAP executables are, where your deep star map is, and where your H-alpha all sky survey is, and then your GPU and or CPU install of StarNet++. So I keep both of them just because sometimes I want to parallelize StarNet++ operations, and you can do that very easily on the CPU, but not it doesn't really make sense to do that on the GPU. So But for this, I'm going to do GPU StarNet so you can see how fast it is. But anyway, so I'm going to run this thing. So it should produce an image every 5 subs. The cold start this, it takes a little bit longer because it's going to do some plate solving and that sort of thing. So you can see it calling plate solve and the plate solve operations in ASTAP here. It usually runs pretty fast in a second or two. This is the second ASTAP call where it's producing those annotations, and that also usually runs pretty quick. And then now it's processing the frames. So it's reading images, flat flame, dark frame corrections, calculating star locations for the registration and dewarp, and going on to subsequent phases. So this thing's going, it's done 4 frames. Here's the 5th frame, and now it's gonna render an image here. So here it's doing that workflow. So cropping, star locations, background and gradient removal, color correction, noise reduction, histogram, and it just rendered the image behind me here. So here's 5 frames at 5 seconds each, I believe, of the North American Nebula, and looks pretty good. No star reduction on this, so this is like Starpalooza here. There's lots of stars, so we'll take care of that a little bit later, but we'll let it run and give it a few more subs to do. So I guess I lost it right here. So oh, it's doing the second render again, and it just did an update right here. And so this will just keep going as long as you do. I think there's about 200 frames of this North American Nebula in there, and so you could let this run for a while here, but we've got other things to do. So I'm going to let this get to the next waypoint here, and then I'll let it finish do this here. And it just did an update. Okay, let's stop right there. Okay. So this was no star reduced processing, but it was still doing sort of the end-to-end workflow. Now let's do some star reduced processing. So all we got to do is change this to 2.0. And if you were a better Python programmer than I, you could write this up in a notebook. So this would be a little bit more elegant, but I just put everything in a cell that is a part of the rendering an image down here. And then I can just do Shift Enter and run the star reduced processing. So this, you'll see the command line give updates right here. It does the same workflow, but then when it gets to the star reduction phase, it will actually do stuff. It'll call StarNet++. So I believe that's running right now. So my GPU is going crazy because I'm running the TensorFlow version of StarNet. So that takes about 20 seconds usually. And then after you've separated your image into your star and star lists, you can do additional processing and more aggressive noise reduction, and you get your star reduced result right here. So, and that's pretty quick. So, if you do StarNet, the star reduced processing, you take an additional 25-second hit to do all of that work. It's still pretty fast. I think, with a modern GPU, like some of the better GPUs out there than what I'm running, you could do this in about half the time. I'm running a NVIDIA RTX 3080, and it's already about half the speed of the top GPUs of today, and it will be even slower by the end of the year. So, but anyway, so that's kind of like AstroComPYute in action. I can show you some more examples a little later, but we'll go back to the talk here and and sort of wrap things up. So you've seen the demo, you've sort of seen what it's all about. It's like this Python scripting approach. You get to use all these cool image processing tools from all those other Python libraries. And your limits on your imagination, and you're not tied to a proprietary ecosystem. So that's sort of the big deal. So where we're at now, as you just saw, you can do sort of that basic end-to-end processing at full resolution in about 15 seconds. And if you add in the star separated processing, you're talking about 45 seconds for the end-to-end process. So that's about the same rate that the data's coming in. If you're shooting 10-second subs, this is just a tad bit slower than that. What would it take to get it to 5-second latency, or to do it like, what everyone would consider to be real time, or definitely near real time. Well, you could obviously bin your data, reduce the resolution in one form or another. That would not only help your noise, but it would also reduce the computational workload. But all is not lost. There's some amazing hardware coming out this year. I don't think we've seen as big of a jump in CPU and GPU performance in a 5-year time frame as we're seeing right now. So the new AMD hardware coming out at the end of the month, and the Blackwell series is going to 2x or 3x processing speed across the board. So it'll be a pretty interesting game changer for doing more processing. But none of this is really taking into account noise and those physics things that we're bumping up against, except for the fact that by leveraging more compute, you can do more aggressive noise reduction, star-separated processing, which gives you options for dealing with noise that you don't have otherwise. So that's sort of what we're thinking about here. But there's another approach, which I mentioned earlier, which is parallel image trains. And this is sort of that dragonfly approach. If you had multiple imaging trains, you could effectively get more subs in the same period of time, and you could conquer the noise that way. I'm really thinking that in the future, this is what smart telescopes are going to start looking like. I bet the next generation, or maybe 2 generations out of smart telescopes, are going to have 3, 4, 5 cheap, 50 millimeter objectives on them, and they are going to have a huge leg up when it comes to noise reduction, because they're just conquering it with sample sizes. I think that'd be a cool way to run a smart telescope. Heck, you could even send the data over the cloud and do the processing on AWS, and then send the result back to your phone. I don't know if people would find that satisfying, but I think it would be pretty cool. I think there's a lot more you could do with this sort of thing. Some things I've been kicking around are like spatially varying deconvolution and deblurring, multi-parameter optimization for automatic collimation and focus. This is sort of getting in the data acquisition direction, but I found a Python API for working with electronic focusers to be able to do this. So I want to give that a shot. There's all sky dust surveys. I've been working on adding that to AstroComPYute so that you could consult all sky dust surveys in much the same ways, and as well as other emission wavelengths. And then doing some like very core computational photography type things like auto stitch mosaics. Technically, the registration algorithm that we use in AstroComPYute can already do this. You just have to give it a canvas big enough and it will auto stitch for you. But doing this in a more seamless way would be really cool, I think. And then dynamic processing, I think, is a really cool approach to doing this near real-time stuff, where early on, when you don't have the sample size, you do more aggressive noise reduction, you do more aggressive binning, in order to compensate for the extra noise. And then as the data arrives, you can increase the resolution, and then you can decrease the aggressiveness of your noise reduction so that you get the really good quality images. But taking this approach sort of gives you the best possible view of the data that you currently have, that you can get away with the noise that you've got. So, well, that's pretty much it. Here's some great resources. I mentioned all these things throughout the talk. There's a story to tell about each of these things. Really recommend this Astro Imaging channel talk, Why Guiding Needs to Die and How It's Going to Happen, because it really inspired me to work on along this way. And if you're interested in contributing or trying this out, give it a shot. It's on GitHub, github.com, Daniel Champion, AstroComPYute. It's PYUTE for Python. And if anyone's interested in contributing, that'd be awesome. Or if you have crazy ideas about what you want to do, or what could be done with this sort of thing, I'd like to hear what you can come up with. So, but anyway, that's pretty much it. I've got some extra content, but I'll pause here because I think we've taken up enough time. But yeah, questions right now?
There are some questions hanging out. By the way, why does all this computation take so long to do?
Yeah,
I'm sorry, I couldn't resist that. Yeah, a couple questions I have, and there are a couple hanging out here, so give us a few minutes. So I think one thing that really jumped off the page was how you did the gradient removal, and we all struggle with that,
Yeah.
even with the new tools. Is there any way to package that up? And I think that Hank Ziegler put in the same question, the thought that I had. That would be a great standalone tool to use on our images, because right now we close our eyes and put points in, or rely on pieces of software that we totally don't understand.
Yeah, no, that's a good point. I like that idea of like making a thing that does one thing well and it makes it usable by downstream operations. And maybe that's a good way to use AstroComPYute, is to make that kind of capability. Especially I've only touched on the star map and the H alpha, but I think especially once the all sky dust survey can be wrangled into that paradigm, that would be a really cool standalone tool.
Yeah, I was thinking about IFN, whether
Yeah.
dust or IFN, because if you go deep enough, it's basically everywhere.
Mm-hmm.
There's no place where there isn't a little dust or a little H alpha. A couple questions that are on here. Let's see. Isaac said, how does your noise reduction algorithm work?
Yeah, I use a few different noise reduction algorithms depending on what stage in the process I use. And again, this gets it into being able to leverage all that's available in some of those other image processing libraries. Noise reduction is not a new problem or unique to astrophotography. Many different fields struggle with it. The ones that I use are the bilateral filters that are implemented in OpenCV perform amazingly well at the linear stage because they don't penalize your stars or any of the data near your stars nearly as much as other noise reduction algorithms do. So the bilateral filter in OpenCV is one of the core ones I use. And then I also use a custom adaptive filter that is of my own design. So I run it on the GPU. What it does is, I think I have an example of it here. So this is an example of it. So this is the Rosette. I think this is 100 seconds of the Rosette Nebula here. I'm not sure if the noise is coming through on YouTube, but this was the original. This is the adaptive filter estimate. And what it does is it has what I call a zoo of footprints. Each filter, traditional image processing filters, typically have a footprint, which is the pixels that it's going to use to perform its operation. And you can choose what that footprint is. You can design custom footprints. So I've created a zoo of about 20 or so footprints of different shapes that all have the same pixel count. And when you run your this particular noise reduction algorithm, what it does is it tests every one of those footprints for every pixel. And one of those footprints is probably better than the others. And you can think about it, if you have an edge in your data, you want a footprint that is contained outside of the edge, not straddling the edge. So the footprint zoo in this adaptive filter approach allows you to find the footprints that match the data very well. And then what it does is it does sort of a goodness of fit test to figure out which footprint is the best or most accurate given the data that you have. And then it estimates the pixels using those good footprints. So
isn't that bordering on making your images match an existing image?
No, not this filter. Maybe was that a comment that maybe was geared towards the star maps and the all sky survey stuff.
No, it just occurred to me when you mentioned
okay.
this.
Yeah, no, this one is more about like, this approach to noise reduction is more along the lines of edge preserving filters. So there's a family of edge preserving filters. The bilateral filter is an example of one. The median filter actually has some edge preserving properties, but it's pretty terrible at it. This one has pretty good edge preserving properties. And really what they're doing is they're looking for footprints that all of the pixels within that footprint give statistical evidence that that's a good footprint to use, as opposed to a footprint that's straddling an edge, and that would look like a bad fit. So it's more of like a statistical approach than matching a known answer, I would say. So good
And
question.
Isaac also asked, can you set your star reduction factor to less than 1? Or less?
I suppose you could. Yeah. The star reduction, I use 2 different star reduction approaches once you have a star separated image. One of them is just like this super quick approach, which is what I call a Gaussian star reduction process. I don't think I have any photos on it because that's another deep tale to describe. Let's see if I have, probably not. But anyway, so one of them is you leverage this mathematical property of stars, which is that they look like Gaussians. And if you take a Gaussian and you raise it to a power, it becomes skinnier, especially if you renormalize it back down to have the same amplitude as it did before. So there's this mathematical trick to do star reduction where you just raise your star-only image to a power, and then you compute an appropriate normalization image, which is based off of the heights of all of your stars, and then you can shrink down the wastes of all your stars. That works pretty good, and that's a fast way of doing it. I also have a that one I think is I didn't come up with that one. That one I learned about on the internet somewhere, but there's a morphological star reduction process that's haven't yet added to AstroComPYute. It's still in beta, but I'm going to add it soon. And that one actually uses a gradient-based approach to shift intensity towards the center of your luminance channel at your star locations, and that has star reducing properties that are outperforming some of the.
So if your stars aren't good enough, we can fix it.
Yeah, that's why I developed that. Is I was actually working on that Rosette Nebula example, and I was seeing some color fringing on that data because I was trying to stretch the hell out of it. And with that morphological approach, you can shift the blue channel towards the center of your intensity center and your luminance channel, and you can shift that data around. So anyway, there are approaches to that through multiple methods. So.
Isaac asked, can we see your extra content? Can we not see your extra content?
Sure, yeah, I can show you some of it. So this is one rig that I've used. So this was at the Rocky Mountain Star Stare. This is my little portable computer. It fits in a travel carry-on case. It's a full ATX desktop computer with a 3080 NVIDIA GPU on it. It's about as small as you can fit an ATX motherboard computer. I kind of had to delete the case, so it's literally mounted to some aluminum rails and a piece of wood, but it works. This was an experimental setup I was using. This is a Canon DSLR, which wasn't the best choice because it's not a cooled camera. It doesn't have the sensitivity that a good cooled Astro camera does, but it gave me access to some really fast glass. This is a f1.2 lens that I was dying to try out. So I got some good images with it, but in the end, you want to go with a cooled camera, kind of like the one that's behind me here. This is a 200 millimeter f2 lens with a cooled Astro camera. That's what took that image of the North American nebula.
Have you ever looked at some long focal length data and see how it performs?
Yeah, I actually started working at f5 and f7 using a longer focal length, I think a 900 millimeter refractor. And it works. It's a different sport, however, because they're working at f5 or f7. Getting good real-time results is not going to happen. For extended objects, you really need to be closer to f2 to get the photons arriving at a rate enough to get really good results in a very short period of time. So, but if you want those zoomed-in images and you want a higher resolution of small objects, you got to go with those higher focal lengths. But yeah, I've used this with a 900 millimeter refractor. That's about as big as I've gone with it as far as focal length is concerned.
So a 4 meter f7.7 is probably not going to work when you're set up.
That's a good question. I think what you'll find is that you might have to use a different image registration algorithm. The image registration algorithms that I'm using are based on fast instruments where there's plenty of stars in the field of view, where you find repeating patterns of stars to do your registration. So when you're at those long of focal lengths, I think your stars might be few and far between. So you'd have to use a quadrilateral approach like AstroAlign or something like that. So
Yeah, also your background maps to do your gradient reduction wouldn't be as precise.
yeah, I think, hopefully your gradient removal is getting simpler as you go in higher focal lengths. Maybe that's a fallacy, but I always thought of the wider field of views as having the worst gradients because of the potential for you to see spatially varying gradients is greater when you're looking at a larger sky. But that could be wrong. It's a good question. So.
There are plenty of gradients in long focal length, depending on where you are and where the moon is, and what altitude you're at. Yes, they are there. Did I miss any questions, Molly?
I don't think so. I think you got all of them. Yeah. Okay.
Well, if there's any there, quickly put them in there so we can get Dan to answer them. But I think we're all mesmerized by what this could mean to us. It's like,
yeah, I've been thinking you should link up with some of the PixInsight folks for the gradient removal algorithm, the Sky Survey informed, because I think that's a stroke of brilliance, and why didn't we think of this before?
Well, on that note, I'll mention that the PixInsight folks have this Mars Pi survey project.
Oh, I did hear about that. Yeah.
Yeah, and they've announced it. I haven't seen any updates on it, I don't think we've heard about the success or the progress on it. But they are attempting to do some kind of survey-based project, especially for gradient removal. But I wanted to do what I can do with the amazing data that's out there already. So
Okay.
Gradient removal is
Did you see the question from Jeff about, is there a user group for this program?
no, I didn't. Is there a user group for this program?
Good job, Eric.
Yeah, currently, if you probably the best I can offer is there's a discussion pane on the GitHub project. So if you want to contribute to the discussions on this, or have some ideas, or you want to use that as a venue to talk to potential other users, I would recommend that. So
Might be worthwhile to set up a Discord server at some point.
Yeah. So.
Okay. If there's no more questions, you can go ahead and stop sharing your screen.
Sure.
Yeah, so that was awesome, and I was glad to get you to come on to the show after seeing your talk at Rocky Mountain Star Stare. And I think a lot of folks on here probably aren't as into the coding side, but there are folks that are, and there's a couple of people who are really excited about this. And yeah, I'm really excited to see what comes next. I might like to contribute to that at some point once I get PhD out of my brain and can do other things again. We're almost there. Yeah, so unless we got any other last minute questions, I'll put out another clarion call for people to come contribute talks. I forgot to mention earlier, if it's a topic we have already covered, don't worry, because there's always updates on a lot of devices and software, and everybody has a different take on how they might approach something. And so even if it's a topic that we've covered before, it doesn't mean that we shouldn't cover it again. So you can go ahead and submit that topic idea for anybody who's interested in coming and speaking on the show. And yeah, come join us next week to hear about the eclipse. And that's about it. Anything else, guys?
Dan, after we close the broadcast, you're welcome to stay and chat if you have a few minutes.
Sure. And
Yeah.
thanks again for inviting me and allowing me to talk on this really cool topic. So I really appreciate the opportunity.
Yeah, thanks for coming on. All right. With that, I guess we'll say goodnight. Take us out. Good night, everybody.
Bye-bye.